Komið sæl og velkomin til þessar innsetningarathafnar sem svo 5. í rauðinni hjá okkur. Við höfum búið til hennar sið núna í vetur að þeir sem hafa fengið framgang eða eru ráðnir til starfa í prófessorsstöður við Háskóla Íslands og við verkfræði og náttúruvísindasvið að þeir séu settir formlega inn í sína stöður. Tilgangurinn einfaldur, hann sá að gefa þeim sem eru ráðnir tækifæri til þess að fara yfir svona sitt svið og rifja upp og fagna árangri en einnig það að hefja svolítið prófessorsembættið upp til vegs og virðingar því að því fylgir ábyrgð og því fylgir frumkvæði og því það horft utanfrá og sérstaklega ánægjulegt að sjá í dag að þetta tilefni líka til þess fyrir félaga, fjölskyldur og samstarfsaðila að koma saman og fylgjast með. Við tökum þetta tekið upp og höfum þetta til taks á netinu og tilgangurinn með því að við getum notað þetta og kynnt fyrir samstarfsaðilum, hugsanlegum og öðrum hvað fer fram við skólann og þess vegna höfum við haft þetta á ensku. Það eina ástæðan fyrir að við höfum þetta á ensku og hérna frá fer þetta fram á ensku. Og í dag þá fögnum við því að Þorvaldur Þórðarsson settur inn sem prófessor í petrológíu og volkanologíu við Háskóla á Íslandi. But in addition to Iceland, he has worked at United States, University of Hawaii, New Zealand, in Australia at Cicero, and the United Kingdom at the University of Edinburgh, and conducted volcano research on modern to Archean successions across the globe, with emphasis on Holocene eruption history in Iceland, tephra studies, lava flow emplacement mechanisms, flood basalt and comatite volcanism, and volcano-climate interaction. He has written more than 100 scientific articles, was the principal editor of ICEI special publication on studies in volcanology, The Legends of George Walker, and co-authored the book Iceland in the series Classical Geology in Europe. On the education front, Þorvaldur has taught university-level courses in volcanology, petrology, and natural hazards, along with range of field courses. He has supervised and co-supervised 1 postdoctoral fellow and 24 postgraduate students in the period 2001 to 2012, and of those, 18 have completed their dissertation and graduated. He is a member of several distinguished international societies in the field of geology, geophysical, and volcanology, as well as the Icelandic Geology Society and the Glaciological Society of Iceland. Personally, I think I would very much welcome Þorvaldur to the university, and I think he's a clear example of that we can still and will be able to attract distinguished researchers and qualified people from all over the world to join us, join the faculty, and I look forward to hear you go through your field of studies and hear what you have to say about the future. Þorvaldur, gjör svo vel.
Good afternoon, everybody. Since it's recording, I'm required to turn this on. Thank you all for coming to this inauguration. It's a wonderful moment to actually have with all of you and maybe share some of the thoughts that I have regarding the task that lie ahead. But what I thought I might do to begin with is to give you a very brief overview of who I am and then what I've been doing since I left Iceland in 1986. So I'm born in Reykjavik in 1958, not very far away from the university. My parents, Þorvaldur and Halla, and I have a sister, Margaret, and a brother. Long time ago, I joined up with Margaret, and we had a son, Jón Þórir, which has produced 2 wonderful granddaughters. And up here is a picture of me and my wife of 18 years. Now, the teenage Thor, he had ambitions very far away from the university. They evolved around something which is actually round in shape, namely football. And, but so in the latter stages of the teenage age, he realized that his temperament wasn't really well suited for these kind of sports. So he decided to do something else, and why not go to university? Geology was what I picked, and the main reason for that is because they offered the most field courses. I wanted to be outdoors and really enjoy the wonderful weather in Iceland on a regular basis. And to make sure that we could get out in the field, we, few colleagues, Jón Smári Úlfarsson and Guðmundur Guðfinnsson, we went out and bought us a 1942 Dodge V-Bon, and we drove around with that for some time. Actually came in very handy in my first research project, which was at the Lucky Fissure. So, as stated, I finished my bachelor's degree here at the University of Iceland in 1984, and that was followed by an honors dissertation, which really started my lifelong commitment and love of the Lucky eruption and the Lucky Conroe. I started this about 30 years ago, and we're still working on it. It has produced 5 PhDs, including mine. But as many young people, you want to explore the world, and for some strange reason, I chose cowboy land and wandered off to Texas and entered the University of Texas at Arlington. So they do more things in Texas than actually use 3D printers for rather strange, to produce strange things. But that's where I did my master's in volcanology, and under the supervision of Professor Stefan Self and John A. Wolfe. And my topic was, no surprise, Lucky eruption. And this is sort of where we made the first sort of complete study of the whole eruption as it took place in 73-84. Along the way, I managed to actually learn a little bit of volcanology and hone in a little bit on my skills in petrology, thanks to John Wolfe. One of the more memorable experiences when I was in Texas was that I applied for a job once with an oil company, and in the job description they wanted someone to analyze the surface morphology of Mount Ararat in Turkey. So I went for a job interview, and after quite some time, the real reason for the job came through, which was actually they were looking for Noah's Ark. So I can actually claim that I've been offered a job to look for Noah's Ark, and I turned it down. But anyway, when time came in 1990 to graduate from Texas, I wandered off even further afield, this time into the middle of the Pacific. I was so fortunate to acquire a NASA Global Change Fellowship. It's basically paid for my PhD research and also subsistence. And because I had that, I could really pick the place, and I picked Hawaii for a number of reasons. My ex-advisor from Texas, Stefan Self, had moved to Hawaii. There was also George Walker, which was at the pinnacle of his career as a volcanologist, and is at least thought by many to be father of modern day volcanology. So I had very good mentors there. And this was complemented by now late John Mahoney, David Berkovici, David Muno, and Tom Holzebos, which has also passed away. Now, despite the fact that I went all the way to Hawaii in the middle of the Pacific, my PhD topic was not in Hawaii. It was in the northwestern part of the United States, primarily working on the volcanology of Columbia River basalt province. And I really focused on one particular event there, which was called the Rosa member, and it was formed in an eruption about 14.7 million years ago. It's very, very big. It covers 40,000 square kilometers, which is a bit more than 1/3 of Iceland. And so, here is the second largest lava flow field in Iceland in historic time. These are drawn to scale, so you can sort of compare it. Likely 600 square kilometers. And of course, the volume is subsequently huge as well, 1,300 cubic kilometers. And the prime objective of my research was really try to understand how these eruptions progressed, what was the typical sort of style of activity, and also try to assess their potential environmental and atmospheric impact due to the gases that they release into the atmosphere. And to our, really to our surprise, but this is something that came out of our research, is that in essence, the lava flows that form the Columbia River basalt, they are actually just very, very large Pahawihoe flows, or Hellurhraun as we know in Icelandic. Some people call them Dyngjurhraun as well. So that's a very important conclusion, because what that implies is that the lava which is erupted at the vents is transported through a system, insulated system, a pathway which keeps the lava really hot. Because if you enclose the lava in rock all the way around, that's a very good insulator. So you keep it hot, that also helps it to become very long. So the Rosa lava flow is about 300 kilometers long, and achieved that basically by flowing through pathways like this, breaking out at the front. And when it broke out at the front, it cooled, and it lengthened the pathway, so it built the pathway as it was advancing. Another key aspect of this work is quite important, is that because of the nature of how the lava is formed, the thickness of what is called the lava crust, the upper part of each of these little lobes that you see here, is actually a measure of time. I'm not going to go into that in detail, but it can actually be used, because the way that crust grows during emplacement is by conduction. And you can actually extract time from that. And so we did that. We measured the lava then in a systematic fashion across the lava flow field, and we came up with a duration for the Rosa of about more than 10 years. So it took 10 years to form that lava flow field. And some of the even bigger eruptions within the Columbia River basalt province, their duration may have been as long as 100 years. So these are long, sustained eruptions. And not only that, during their whole eruptive period, they're pumping out a lot of gas into the atmosphere. Some of the gas is not very nice. We focused on chlorine, fluorine, and sulfur. So if you look at the sulfur emission from an eruption like this, it will carry about 30,000, between 13 and 14,000 megatons or million tons of sulfur dioxide towards the surface. Of that, about 12,500 is released into the atmosphere above the vents, and it then carried up, a part of that is carried up by the eruption column up to 15, 20 kilometers into the atmosphere, and then dispersed away. And so the total loading of the eruption in terms of sulfur dioxide is roughly about 10,000 million tons. And when that sulfur dioxide reacts with atmospheric vapor, it converts into little droplets, which we call aerosols. And Rosa could have produced about 15,000 million tons of sulfuric aerosols. The importance of those aerosols is that they actually basically represent fog. So you will have a plume that is dispersed somewhere between 10 and 20 kilometers widely around the globe, and it's almost a complete fog. That will block out the sunlight and cause surface cooling. It also will have an impact actually on the atmospheric flow, the currents, atmospheric currents and the winds. So it actually will have a significant impact on the climate. And some people would argue that an eruption like this might be enough to actually trigger changes that would result in mass extinctions. Now the numbers here in the brackets below, that is the amount that the Laki eruption in 783 put out into the atmosphere, just for comparison. And we know from historical records that the haze, the plume from Laki, caused a cooling of about 1.5 degrees over a period of 2 to 3 years. And it also caused significant atmospheric pollution that affected people widely, including Europe and North Africa. Now, of course, all good things come to an end, and the wonderful time I had in Hawaii as a PhD student ended in 1994 when I defended, and I was fortunate enough to have an offer to do a postdoc in New Zealand with Bruce Houghton to work on the White Island volcano. Now, I should add that none of these were planned. But it's not like when I left Iceland in 1986 that I planned that I would actually start on a journey across the globe. I always anticipated I would go back. But this is how things develop sometimes. So this is White Island. It's an island. It's about 50 kilometers offshore of the North Island of New Zealand. It's about 2.5 by 1.5 kilometers in diameter top. But below sea level there is a big stratovolcano. So this is basically just the summit. And it's an active volcano. And just to sort of measure on my intelligence, I camped there for a week when I was doing some of my work. I also camped over here for another week. And not realizing until afterwards that this is probably the most stupid things you've ever done. To actually raise a tent in an active crater. But anyway, we managed to get through. Objective of this work was to really look at the products of eruptions that took place between 1986 to 1991 at White Island. And for the first year, I made a good progress on that, and as well as mapping the structure. But towards the end of '95, I was quite interrupted by activity at the biggest stratovolcano in New Zealand, on the Ruapehu. And this is just some shots of that activity. Ruapehu started erupting on 18th of September in '95, and when that happened, Bruce said, okay, stop working on White Island, you're going to be part of monitoring this eruptive activity at Ruapehu, which was a wonderful experience for me. It really got me into sort of monitoring activities. I learned a lot from these guys in terms of how you go about work when you are monitoring both from instruments on the ground and also on the volcano. But it's actually quite a sustained activity. It lasted into 1996 with the biggest eruption at about 6 o'clock in the morning on the 17th of June, 1996. And it so happened that I was actually in a helicopter when that eruption started, and we got actually pictures of the beginning phase of the eruption. I should also add that I've never spent as much time in a helicopter as I did during those 2 years. And that's probably the most dangerous activity I did in relation to the activity that we were facing. When you're flying helicopters up to summits of these volcanoes, they're not the most trustworthy transport, really. But one of the key things that came out of this work that we did at Rope, besides giving people warning and informing the authorities about how the activity was going, is both on White Island and also for Rope, when we did the petrological studies, we looked at in detail how the rocks are made up, what the chemistry is, etc. We came to the conclusion that there was no good, well-defined magma chamber underneath either of these volcanoes, and the magma that was erupted came from very small pockets of magma in the shallowest part of the conduit. And each of these eruptions actually came from different pockets. It was quite an interesting result, and actually it explains a lot of things about how these volcanoes behave. For example, this lack of inflation. We didn't measure any inflation except for just a little bit of the very, very top. So they were sort of quite useful in that regard. But on we go. I was on a 2-year contract in New Zealand, and when my contract was coming toward the end, there was rather harsh economic times in New Zealand, and the institute that I was working at, IGNS, was actually letting people go. And I said, what are the chances that I will get an extension on my contract? They said very little. So I started sending out applications for the jobs. And that didn't go too well until I got a call from Perth, Australia, as they say in Scotland. But as they pronounce it in Australia, they say Perth. And I got an offer from CSIRO, the Mining Exploration Division at CSIRO, to come to work as a researcher in applied volcanology. And which I took, and off I went. The newlywed Thor went off to Australia to take on this new job, and he basically went from literally the youngest rock on planet Earth at the time to work on some of the oldest rocks that we have exposed at the surface. And when I landed in Perth, my colleagues were very nice. They said, we will plan an excursion out into the bush in Australia to show you the best outcrops, show you the field. And off we went, 600 kilometers in the bush, and then we walked for about an hour or so, and then they suddenly stopped at a pile of rubble. And I said, why we stopped here? They said, well, that's the outcrop. And I stood there for a while and wondered, what have I got myself into? And then I looked at the rocks, and they all looked the same. They all had the same red, rusty appearance. They were talking about this is this type of rock, this is rhyolite, this is ultramafic rock, and I couldn't see the difference at all. A few months later, after very good mentoring by my boss Rob Hill and my colleagues Steve Barnes and Terry Mattox, I was talking just like them. I looked at these red, rusty rocks and told people that this was rhyolite and this was ultramafic rock, even though they're very different in chemistry. And not a bit of it, we were actually right. And then we spent a lot of time logging. We logged about 15 kilometers of core, 169 diamond drill cores at the mine site, the tenement of Black Swan. This was a project that we worked for NPI Mining Company, and we produced this kind of cross-section. And I'm not going to go into detail. I can tell you the yellow ones are the rhyolites, the green and the purple ones are the ultramafic rocks. Now, why are they interested in this? These guys, they are looking for nickel. They are mining nickel. Their interest is just to extract nickel from the ground. And this nickel is usually found in ore bodies which are very rich in sulfur, shown here in red. Actually, they're right there. I enlarged the inside here just to be able to see it. Well, that was the body that they were mining at the time. We constructed the geology there because they wanted us to develop a geology-based or volcanology-based exploration model that would allow them to target new ore within this sequence. And so we did. we mapped it out. We also figured out that basically these ultramafic lavas or komatiites, which are very silica-poor lavas, they primarily consist of olivine, the mineral olivine. When they erupt at the surface, they're very hot. They're between 1200 and 1600 degrees. And they come up to the surface. And thus, because they're so hot, they can actually erode, thermally erode the surface they flow over. And as it turned out, when we had worked out everything out, these also turned out to be just typical Pahawihowi lavas or Hetlerhraun. Very large ones. And more importantly, they had two different sort of suites or two different appearances. They had what we call flanking lobes, which are similar to what is shown over here. But then they have what we call a pathway, which is basically the tube that I showed you earlier, the transport system. And this is quite important to be able to distinguish between these two because the ore that holds the nickel accumulates in the pathways. So when you want to target things, you want to find the ore, you look for rocks that tell you that you're actually in a pathway, and then you continue. And the success of this model, even though it's reasonably simplistic, the success of it is enormous because the Cosmos mine, which has been was just closed this year, but it's been in operation for the last 30 years, it was basically founded on these principles. That's how they found the ore. They used our exploration model. So volcanology can actually be useful in mining as well. After 5 years in Australia, I started missing those young-looking, youthful rocks. So I said, I've had enough, and I gambled quite a bit. I went and took what we call a soft money position at the University of Hawaii. I was very glad to be back, able to sample hot lava flows and see my favorite volcano, Mauna Loa. It's also the biggest volcano in the world. And but I couldn't spend much time in Hawaii on the islands because the research that I got funded for took me out to sea. So I was involved in 2 cruises, ocean program cruises, and spent 2 months out at sea, for example, when we were drilling into these mountains, subaqueous mountains, which are continuation of the Hawaiian island chain. So the Hawaii is over here, and these are all volcanoes that have been formed over the last 120 million years. And the reason why they form a chain is because the plate is moving over the active area and takes the volcano off its source. So it basically cools down and freezes, and you form an island chain. Why were we going out to sea to drill this thing? Well, the leader of the expedition had put forward the hypothesis that mantle plumes were not stationary. And this has a big implication for how we understand how the plates move and plate tectonics in general. Up to this time, people had assumed that mantle plumes are stationary, and they were used as a reference frame for all plate movements. We went out to sea, and to make a long story short, we found out that Hawaiian plume over the last 120 million years had actually moved 70 degrees latitude. So roughly about there to there. So at least the Hawaiian hotspot is not stationary. There's been a number of other cruises since then which have gone out to test this hypothesis, but the results are not out yet. In the middle of this, being on soft money, what it means is that you have to raise all your salary yourself. And that's very hard in a competitive environment. And I was very fortunate. In 2003, I was offered a half-time position at the University of Iceland, which I took, so I spent half of my time in Iceland until 2006. And went back to looking at tephra layers, and also sort of started investing more time in looking at the Laki lava flow, and also rootless cone groups that are within the lava In 2006, I was lured to Edinburgh to take up a post in volcanology and natural hazards at the University of Edinburgh. And I don't want to really spend too much time on this, but as a result of that, the focus on my research was entirely Iceland. And these are just some list of some of the projects that we've been doing, and we've done some really exciting work in places like Grímsvötn, Askja, and Eyjafjallajökull, etc. It's been a very good time. Now I'm here. So, what is my real interest and where do I think we should be heading in the near future? Well, as you might have figured out already, I'm really interested in a very broad perspective of how volcanoes work. And basically, from the bottom to the top and into the atmosphere, the whole system. It's a very complex system, and it's all interlinked. It's very difficult to understand it completely unless we have a good understanding of all components. And there's no way we can do that without multidisciplinary research. What I mean is that we have to get specialists from a lot of different disciplines or different fields to work together collaboratively and try to figure these things out. I just want to mention a few things about these things. As an example, if we look at the lower part of the system, people have generally heard quite a bit about volcano monitoring. And volcano monitoring really is based on detecting, prior to eruption, what's happening in this deeper part of the system. And it basically detects changes in earthquake activity, surface deformation, or gas emissions from the volcano. And of course, these changes are related to what the magma is doing in this deeper part of the system. Now, it's an important thing to remember is that magma is a very complex fluid. It's not a simple fluid. It's not like water. It doesn't just freeze at one temperature. It does not have a unique freezing point. It actually solidifies over a range, a temperature range, and it can be a mixture of liquid or fluid, crystals or solids, and gases. So it's a polycomponent and multi-phase. And all of these things, they actually make this whole equation a little bit more challenging, but also more, in many ways, more exciting to deal with. And just to sort of iterate here, so earthquakes, deformation, gas emissions, they are really derived properties. So what we are actually detecting and trying to use to tell us whether the volcano is going to erupt or not is something that is a consequence of something else. And that's the best thing we have. But one of the things we probably can do is try to understand it a bit better. And one thing we do know is that it depends largely on the magma properties, the plumbing geometry, and the strength of the enveloping crust which is around. I want to focus a little bit on the magma properties here because they're important. This is an image of a magma chamber, if you like, or magma storage system, and which shows that a system like this is not just fluid. It's not just pure liquid. It can consist of a mixture of liquid and solids, and to a variable degree. So it can be mostly fluid in here and more solid to the edges. The fact that you have that also means that the properties of this magma is very different here compared to there. And the exact nature of this will depend on actually how this system will respond to new injection of magma into it, and also will have an impact on how that releases magma. We need to understand this a bit better, and especially if we want to be able to forecast eruptions. We have to understand the relationship between magma properties and magma movement versus that of seismic deformation and gas signals. We have to find that link, and that is not an easy task, but there's a number of projects, ongoing projects that are aimed at this now, And this is a very exciting avenue of research in the future. I think it will generate a lot of both interesting results and a lot of opportunities for especially young researchers. So we need to collaborate if we want to really achieve this. There are some new methods that have emerged in recent times which are providing us with the opportunity to actually probe, take a sample at the surface, look at that sample in detail, and actually obtain information about what was happening deeper in the ground. And the examples I'm taking here are really focused on these little white blobs here, which are the crystals, which have grown in the magma at depth. And these crystals are not as simple, they're actually complex. As you can see, they show distinctive zonings, and so they actually have layers which have different composition, but these layers, they grow at different times, just like tree roots. So basically, you have really opportunity there to actually go back in time. The youngest one is out here, the oldest one is there. And people have started doing this, and this requires very special techniques. You have to have tiny little drills, because you're actually talking about something that is micrometers in diameter. And you have to have very good analytical tools to actually be able to analyze such small samples, the precision required. But down here, what we show here is actually the x-axis here shows number of analyses, and this is just an arbitrary isotopic ratio. And what it is illustrating is the difference in results. If you take all of these 4 crystals, you analyze them together, you get a result like that. And basically what you've done, you've averaged the whole thing of these 3 zones here, so you get some sort of an average. That doesn't really tell you that much about how the crystal formed. It tells you what its average composition is. It doesn't tell you anything about its growth history. Now if you take individual ones, each one, and analyze them as a whole, you get a slightly better result. You start to see differences between the crystals, but still you're averaging individual crystals. So you're averaging time, really, in each crystal. Now if you analyze individual zones, then you start to see actually quite interesting things. You see differences in the zones in terms of their composition, and within each individual zone you get a very uniform composition. Now we actually got back to some real information which is telling you about what, for example, the core here, where that was growing, what was the composition at that time, and then composition of the rim, which is very different. Different environment. Now we can start tracking the magma, how it is actually moving, how it is moving as it's evolving. Getting information about its movement. This plot down here is slightly different. It uses the zonation in the same way. If you start with a crystal that starts to grow out of magma and uniform conditions, it will have a very uniform composition. Now if you move that crystal to a new environment, either by magma mixing or something else, you change the conditions and you have a zone that grows out of it which will have a different composition, but it's in equilibrium with the new environment. Now this crystal sits in this environment for a little while. Because of the compositional differences between these two, what the crystals try to do by diffusion, by moving individual molecules backwards and forwards, it tries to equilibrate itself, make itself uniform in composition. So molecules are moving over there and back out there. And that's sort of shown by this diffusion profile. So you start to smooth the differences out. Now you have an eruption. The exact shape of this profile actually gives you time, the time scale. And you can actually start to extract information about time, actually when these particular processes were taking place. And when you have that, then you can start to tie that with seismic activity, inflation periods, and other indicators. Now you're starting to get some information about how what is the property of the magma, how it's behaving, and hopefully in the future we can actually tell something about what it will do, hence forecast. Unfortunately, it actually is fairly expensive. It requires very specialized analytical equipment, which is both expensive to run and expensive to use. I know I'm running short on time here, but just really quickly about shallow conduit, the uppermost part of this plumbing system, the part that is closest to the surface, but can extend 2-3 kilometers below the surface. This is actually the most important part of the volcanic system in the sense it determines the native style and power of the eruption. Things that happen in this environment, they really control this. Now, they can be influenced by second order properties from the deeper system, for example, how much fast the magma moves up. But the key to whether we have an explosive eruption, whether we have a really big explosive eruption, or whether we have just a lava-producing eruption, is hidden in what happens in this part of the system. This is the place where you actually, the magma, which at depth is a liquid, it maybe some crystals in it, gas dissolved in it, it changes state. It actually goes from being a liquid to a liquid with bubbles in it, or foam. Eventually it goes into being a system which is gas and particles. And as it does that change, it really accelerates out of the vent, and that's what determines the explosiveness. This is just another way of sort of showing that. So here it is liquid, here's the bubbly liquid, and here it is gas, the particles in suspension. Now how you do that is also important. Just as an example, if your system actually starts with deep boiling, so you start actually exhausting gas relatively deep down in the conduit, and it's a continuous sort of a degassing, gas streaming into these bubbles. So it's basically continuous boiling. There's a possibility that we might have a more sustained explosive eruption than otherwise. Now, if the magma rises fast enough that actually it doesn't have chance to actually start its boiling down here, it actually then gets super critical, or super saturated in gases, and you have a flash on boiling, you might have a very powerful but short eruption as a consequence. Just as an example. And actually, time scales are very important here as well, because we're not talking about something happening in hours, or we're talking about something that's happening in microseconds to seconds. I'm going to skip this one. The reality is that in Iceland, research into processes that operate in the shallow conduit is basically in their infancy. If we want to be able to predict style, size, and intensity of eruptions, or even forecast those things, then we have to improve our knowledge of shallow conduit processes. We have to really focus research on that aspect of the system. And again, that requires not effort by an individual, but a collective effort by the community. Yeah, we're getting very interested now. Humanity. When we get to the surface, things change quite drastically. Now you're talking about material that has been expelled and deposited on the surface of the Earth, and people quite often get in the way. And I should just very briefly say, volcanoes produce almost all geological hazards that we know. Some of them are direct, others are indirect, and just very quickly, we can have lava flows coming out, whether they're lava domes, that then can collapse and generate pyroclastic flows, or just fluid lava flows, basalt decomposition. We have tephra fall, as we know, from 2010 and 2011 eruptions. They can have an impact close to the volcano, also thousands of kilometers away from the volcano, and the most widespread impact. We can have pyroclastic density currents produced by these things, which can be very devastating because these are really hot gaseous clouds that move at velocities of plus 200 meters per second. And if you happen to be in their path, that's end of story. That's an example of one right there. Volcanoes also can produce lahars, and they can be quite devastating. Mount Pinatubo, which erupted in '91, produced a very powerful explosive eruption which killed about 8 or 10 people directly. Now, it deposited a lot of material, loose material, on the volcano. Subsequent in subsequent year, the rainy season, all that loose material was remobilized and moved down as mud flows or slurries. And these mud flows or lahars killed more than 80 people. Gases, as I said earlier, they can actually, they're quite widespread, they can be more widespread than the tephra fallout, they can stay in the atmosphere for up to 2 to 3 years, they can cause severe pollution, they can result in surface cooling, they can also modify how the atmospheric currents flow. And just to read, we've done a study, we modeled a like eruption today, and asked the question, what would happen in Europe if we had another like eruption? What would the pollution that such an eruption would generate, what would that do? And the result indicate that it could kill up to 130 to 270,000 people in Europe, just from the pollution. This is not talking about cooling or anything, just breathing in that sulfuric gases. Now, so we got plenty to do in the future, because not only we have to understand all these processes that I was going through, we probably also have to be able to predict them or forecast them, especially in the light of ever-growing population on planet Earth, which basically exposes more and more people to natural hazards on a daily basis, really. Teaching, one slide, and I'm done. Fortunately, I won't have much time to say about teaching, but what I want to say is, Earth's history is really written into the rocks and into the sediment. This slide like this, that is actually basically documentation of a particular process that took part in forming our planet and modifying it. And basically, one of the more important tasks as a teacher is that you have to teach, as a teacher in earth sciences, I should say, you have to teach the students to actually read the language of rocks, including all the local dialects. And I think teaching needs to be hands-on, interactive, and dynamic. There are many ways you can do that. You can do that in a laboratory, you can do that with exercise, you can do that with designing a project that involves industry. Basically, I think the easiest way to teach a carpenter to use a hammer is actually to give him one and have him using it. I think the same applies to earth sciences. Thank you.
That was quick. Very thorough. Thank you, Þorvaldur. I've got a dying question. Are you looking for new signals or new signs or markers in your studies, or do you think to evolve the field further? Are you going to use the current skills and current markers that are available?
Well, they will always. What we have now and what has gone before us is always going to be the foundation, and we built on that foundation. Now, you always hope as a researcher that you will find new avenues and you will develop new methods that will produce innovative insights into the process that you're looking at. So, but I think, as always, in all science, is that you always stand on the shoulders of your predecessors.
So you're more looking for to use what actually been built. You're not waiting for new
markers. I want to use what has been built and use it better. But I also want to look at the possibilities and the options of using new things or developing new things, whether that is in terms of instruments or intellectual approaches to solving problems. And it's an evolving field. I mean, science is always evolving. You have to be progressive in your approach to things.
Fire away, please. Go ahead. One question for Þorvaldur. Good day. Magnus.
I will probably use the hammer more than the screwdriver. I have to admit. It's been a handy instrument in the past and very effective.
The hammer on your head. And the shovel.
The shovel, you can't forget the shovel. It's an essential tool. And a measuring stick. See, that one of the things that people always talk about, field work is qualitative. And I think that's a big misconception. When you do field work, you actually do a lot of measurements. And using it as a simple measuring stick is actually more quantitative of a measurement than many model calculations that we see being published today.
Can I just put, you've been traveling all over the world, and do you really, at the end, believe that we here in Iceland can do something, that we have a potential to do something in glaciology, except that we have volcanoes, and we are flying over volcanoes whenever they erupt and all that? That's the main work so far in volcanology in Iceland, isn't it? Well, what is the potential? What is the potential?
I wouldn't describe it as such. The field is changing. There's a lot of potential. We're doing a lot of detailed studies and measurements, which both involve the field and also looking at deposits, at characters and deposits, and using that to actually infer about the process that drives the volcanic eruptions. So, and a lot of these methods that we use are not expensive ones. You know, you can do a lot of really useful measurements for, if you have a computer, you have the right imaging equipment, etc. So, yes, I think we can. But to do good science, you don't, having expensive equipment does not guarantee that you do good science.
Hammer is enough.
Sometimes it is. And my old professor, George Walker, said once, met him in the hallway, by accident, he was just walking and I was walking in the opposite direction, and he stopped as he came to me and he said, do you know, there's a lot of geology to be done with a pencil and a notebook. And I still stood there for a while, but,
Bryndís?
Well, Þorvaldur, you know, as you, I'm interested in volcanoes, but I monitor them, you know, with different mythology. And I guess you were kind of proposing to us seismologists that we have to get together and try to study the, you know, the internal structure of volcanoes. And I can tell you it's very difficult. And but I always think of volcanoes as dogs, you know. Some of them, they don't. Some of them bark all the time, meaning earthquakes, and they don't erupt. And then others, they're very quiet, and then they attack you without any warning. And so, being, you know, having traveled all over the world, you probably and seen so many different volcanoes, I would like to have your opinion of how we can actually, on an international basis, you know, join forces in trying to understand all these different volcanoes, which are like different types of dogs. And actually, I know here in Iceland, through the Volcanological Institute and these international collaboration of volcanologists that we've been doing, you know, we've been doing that. But I would like to, you know, hear what you foresee in that direction.
yeah, I think, you know, to begin with, I think we should focus on one dog at a time.
But they don't, you know, all erupt.
No.
All erupt at the same time.
I know. There's one thing is the monitoring side, and we really need to keep doing that and work towards improving that as we're doing. The other side is to improve our knowledge of A, the structure of the volcano, B, the physical processes that are involved in the eruptions at individual volcanoes. And that means that you have to study a number of eruptions because there's a whole variety of them. But at the end of the day, what we want to be able to do is to reconstruct a volcano and its processes in as much detail as we can. It's not going to happen overnight. It's going to take probably three or four generations to get there. But we have to start somewhere. And I think the best way to start that is if we do sort of a cross-discipline studies where we actually effectively communicate and talk about our results. You know the seismic activity better than I do. I mean, I can't tell you anything about that, but I might be able to tell you something about magma properties. And when you look at your seismic stuff, and I tell you what my magma is doing, you might then you could say, that's maybe why that seismic activity is different here than over there. So I think that's on a very sort of a fundamental basis, I think is the best way to start. But we need to understand better the behavior of magma as it is coming up through the plumbing system. And I think that's one of the sort of the caveats in our knowledge. That's where we know the least. And I know it's not an easy task, but we shouldn't give up because it's difficult.
We never give up.
Sigurður.
Thank you very much, Þorvaldur. It was very enjoyable and nice to see your travel back in time. I think what is very important about your career is that you posed important questions. And you posed important questions for important processes. I mean, you took the largest eruptions, and that is, I think, one explanation for why your work has had such a huge impact. So that's very important. So I guess, and for those of us that are at this critical age in our life now, is that there's a limited time left. It's important to find important questions to focus on. So as far as I can decipher from what you're saying here, that the question that is very important is the surface process. It's basically when you are in the process of producing the tetra and how you form it in the shallow process.
I think that is one of the biggest questions today, because that's where we know the least.
And also there's a lot of connection there with humanity there. I mean, in air traffic, I mean, I think Eyjafjallajökull had really changed our attitude. You know, it's kind of before and after Eyjafjallajökull.
It most certainly did. I mean, if someone had asked me, you know, on, let's say, 12th of April 2010, that a small explosive eruption at Eyjafjallajökull could close the airspace over Europe, I would have said, no, that's not going to happen. But it did. But that just tells us also is that, you know, there are certain things that we know very little about. And Eyjafjallajökull eruption is one very good example where we actually, most of the things that happen are probably related to processes in the shallow conduit, but we don't know exactly what they are. And you know, the plan is to try to find out in the near future. But that's where the real, you know, now I'm getting people to take, that's where the properties of the magma as it's coming up to the surface changes most rapidly. And that is the key, I think.
If I might pick on this, I think it was Magnus Tumi who said that in the south area of Iceland alone, he thinks there are about 1,700 geophysicists living. And I want to ask you, this is the most popular science, I think, in Iceland, always been, geology and geophysics, even almost more than weather.
I think it's seismologists.
Yes, seismologists. And
well, especially now when they can look it up on
exactly.
On web.
How in your field, how important is that to the general public, and how do you see opportunity in activating that or relating to the field with the general public in Iceland? And
yeah, I think, you know, there are two aspects to it. I mean, I think in one thing it helps with, maybe we'll start with that, their interest in the natural sciences, this general interest, actually is hugely beneficial when it comes to dealing with a disaster, because these people actually at least have some knowledge.
yeah.
Also, they can be, I mean, there are aspects of, especially of sample collection, especially tetrafall and things like that, where they could be, you know, active there and have been activated in the past. We could probably do more of that, and it would make our job much easier. But I also think, you know, involving, you know, the general public in, you know, exercises and activities related to doing research is a good thing, and I think we should promote that.
Páll.
Yeah, I would like to thank you for a very inspiring lecture. I think that it's food for thought for a long time. I would like to disagree with one statement you made, and for a reason. And you said we should study one volcano carefully. And first of all, I don't think we have a choice. We study the volcano that's doing the most at the time, and we can't really pick that, so we have to study what comes along. And secondly, even if we had a choice, I don't think we should. I think one of the really benefits of being in Iceland is that we have many volcanoes to study and many different types of volcanoes to study. And if there is anything in our studies, then it is one of the conclusions is that they're all different. So, so taking the analogy of psychology, we would probably not learn very much about humanity if we studied just one person. And we have to really look at the whole population. And I think that's what we really should concentrate on. Of course, we have to study them carefully, but I don't think we should limit ourselves to single volcanoes.
Yeah, I
we
think
should really take the whole thing.
No, I think, probably I did not say this correctly. In a way I was saying maybe it would be useful to focus on one dog at a time, is that for a group of scientists it might be useful to try to dissect and try to get as much information about each volcano. It doesn't mean that everyone should be working on it. If we have enough people, then we could have groups working on all of them. And I agree with you, we should work on all the volcanoes. We should be looking at all of them, because all of them have their own personality, so to speak. And there are differences between them which are could be related to a host of things, slightly different crustal structures, slightly different geometry of this and that. So we should be looking at the whole range. I agree with that. But there was sort of I was just imagining having all these dogs around me barking. It might be easier to deal with one at a time.
Það ekki fleiri spurningar, þá held ég að ég hræðist þetta guðurlæsina hérna fyrir. Þetta svolítið hamfara spá sem þið komið alltaf með. Það er ekki að bíða boðunarleikur og fara að fá okkur breytrar og þetta áfram. En áður en þá vil ég færa hérna þessa bókagjöf. Takk fyrir og velkomin til starfa í öfluga sterka sögu og sterka hóp sem hefur mikla skiptökum í okkur og gott að fá þig og við hlökkum til frekari afleika. Og svo bara eftir spyrja hvaða fótboltafélagi þú ert að spila með.
Ég verð að segja Stjarnan.
Velkomin til
Takk að þér.